Welcome back to my rubber heart. Today we are diving into a fundamental but fascinating aspect of rubber science: how certain additives like antioxidants, antiozonants, waxes, and release agents actually move or migrate through the rubber matrix to where they are needed most. It's a complex dance rooted in chemistry and physics and essential to rubber performance. First, picture a freshly compounded rubber. It's loaded with additives like antioxidants to prevent heat-induced aging, antiozonants like 6-PPD to fend off environmental attacks, waxes to form protective surface films, plus curing agents and processing aids. Initially, these ingredients are evenly distributed, but then something begins to happen. Surface reactions like oxidation or ozone exposure deplete these additives at the interface. As soon as even a small amount of antiozonant reacts and vanishes, a concentration imbalance forms. Inside the bulk, there's more of the additive. At the surface, there is less. Nature abhors such gradients, and so diffusion kicks in. Additives begin to migrate towards the surface, moving down a concentration gradient until equilibrium is restored. Once added back, they can continue protecting the rubber against further degradation. But what governs how fast and how far these molecules can travel? A few key factors determine this. The first is molecular size and weight. Smaller molecules, like many antiozonants and low molecular weight antioxidants, diffuse faster. The rubber's glass transition temperature and chain mobility also matter a lot. Rubbers with lower Tg allow additive molecules to navigate more freely. Next comes chemical compatibility, often understood through solubility parameters. Each compound, polymer and additive, has a Hildebrand or Hansen solubility parameter, which measures cohesion energy density. If the additive and rubber have similar values, the additive dissolves more easily, migrates moderately, and doesn't bloom or stay locked in. In contrast, poor compatibility causes either rapid blooming, where additives separate uncontrollably, or no migration at all. Additives that aim to stay within the rubber long term, like stabilizers, are chosen to have a moderate mismatch, resisting migration. Those designed to replenish the surface, like 6-PPD or waxes, are chosen for balanced mobility. Here's an example from research. Scientists have measured diffusion coefficients in tire compounds and found waxes migrate at roughly 10 to the minus 16 to 10 to the minus 18 square centimeters per second, while small amine antiozonants diffuse faster at 10 to the minus 12 to 10 to the minus 13 square centimeters per second, enabling visible migration and bloom on sidewalls. Modeling this behavior comes down to Fick's laws. Fick's first law tells us flux is proportional to the concentration gradient, while Fick's second law describes how concentration changes over time. The key variable is D, the diffusion coefficient, which itself depends strongly on temperature, polymer mobility, and molecular size. Now, why is all this important in practice? Take antiozonants like 6-PPD. They work by migrating to the surface, consuming ozone before it can damage the rubber chains. As they're used up, more migrates in, providing a renewing barrier. Without migration, you'd have high interior protection, but no surface defense, and that is where destructive cracking happens. Waxes, too, play a big role. As they bloom to the surface, they form a physical barrier, blocking ozone and UV light. That is why fresh tires sometimes show a waxy sheen on sidewalls or entire tread cracks. The wax layer is protecting your rubber. We even rely on controlled blooming of release agents in molding, ensuring rubber doesn't stick to metal tooling. But migration isn't always beneficial. Too much can lead to blooming, leaving unsightly powdery surfaces. Too fast, and antioxidants can exhaust early. Too slow, and the surface goes unprotected. The cure is compound design, balancing molecular weight, additive polarity, rubber glass transition, filler load, and cure chemistry to fine-tune migration rates. In advanced research, scientists use molecular dynamics simulations to model additive diffusion, computing parameters like mean square displacement and solubility parameters. They run virtual rubber models with additive molecules, watch how they diffuse, and predict performance, sometimes even matching lab data on aging and migration. By understanding these models and data, compounding scientists can forecast how an antiozonant will bloom after 6 months on a shelf or how long a wax layer will last in desert heat. They adjust formulations accordingly, choosing higher molecular weight versions for low migration longevity or faster diffusing waxes for quick initial protection. In short, what seems like simple migration on rubber surface is in reality a finely balanced symphony of chemical design, polymer physics, and kinetics. Antioxidants, antiozonants, waxes, and release agents, they are all choreographed to move when needed, protect when needed, and stay invisible when not. The next time you see that subtle sheen on a new tire, know that there's intricate science at play. Molecules moving, defending, and replenishing in service to performance and safety. Thanks for watching, and I will see you in the next episode. Until then, stay elastic and stay curious.